Okay. So today we're going to be talking about sequence models. Yeah, so like a little bit of motivation for like why we care about sequence models. Technically, there's a lot of different things that relate to sequences. You have things, like the weather. The second image on the left is a spectrogram for audio, so you can see the frequencies at every single slice of time. But images, if you think about it pixel by pixel, like one after the other, unrolled, it's technically a sequence. And more recently, there have been a lot of architectures that have treated images sort of similar to the way that people treat sequences. So it is of interest to us, and will motivate some of the lectures that will come like tomorrow and the day after. So for the next 2 weeks or so, we're going to be talking about image processing and image recognition from sort of more of a sequence modeling perspective. So yeah, so that's why we are talking about sequence processing today, even though this is a computer vision class. So we're going to talk a little bit about how we represent sequence data. What are the goals that we would like out of a good sequence model? We're going to talk about like a simple solution for that, a recurrent neural network, and then a little bit of fluff at the end, embeddings and positional encodings. So yeah, let us jump in. So sequence data. So like the most basic form of sequence data is like time series data, where every single time step, we have some data recorded. So an example for that is like weather, right? You can record like temperature over time, cloud coverage over time, where every element in your sequence is like a different image. Yeah, time series data is definitely the most common. Yeah, so you can have music and audio is another one. I think later on we have one person who's really interested in like audio generation, and we're going to try and loop that in with like a lecture on like deep fakes. So we'll talk about audio generation like a little bit more later. Yeah, like sound is just changes in air pressure at different steps in time. The only problem with sequence data being, generally speaking, we have too many samples per second. Like audio data sampled at thousands of times a second, and that's not really easy to process, generally speaking. So yeah, like for audio, more practical representation, it's like a spectrogram where you have larger slices in time, and where for that little slice of time you record all the different frequencies that are present. Yeah, it's sort of frequency decomposition is not something we're going to talk about too much here. It's sort of a weird thing, like if y'all know what a Fourier transform is. But the takeaway with music and audio is, in order to practically represent it and be able to process it, we need to figure out how to compress this huge number of samples down into like a more reasonable number of time steps without losing a ton of information. And like an important thing with like audio generation or audio representation, yeah, is just how do we figure out how to more like practically represent it. And that's sort of something we've talked about like before too. Like how we represent data really does matter. And the same is very much true in time series data, which is kind of what I wanted to get to. And then the last most common form of sequence data is like text. It's pretty much everywhere, just because it's so easy to just like scrape the web and just get access to huge amounts of text data to train your models on. So yeah, just like internet scale language models are a thing, where you have language models that are just trained basically on just the open internet. Every single word is like a token. It's one of the elements in your sequence. And in the simplest form, you can just represent every single possible word as a one hot vector, just to ensure that every single word is sort of like the same distance from each other. Like we talked earlier about why we don't just represent the output of our neural network that's classifying digits as being just a single scalar like 5. Why do we not have our model output this? And it's for the same reason, like, well, what if our model's not sure if the output is a 5 or a 7? Should it then output a 6? Because that's halfway in between. Like, no, that's less expressive. And for the same reason, we don't want to have words being represented by the index in the dictionary, that they're located at. Like if Rome is like the 5,000th word in the dictionary, and then the 5,001st word is like, instead of Rome, maybe it's rum. Those words maybe don't necessarily, there's not like a meaning associated with the fact that they're really close to each other. If we represent our words as one-hot vectors, the distance between any two vectors is always the same, which is why this is frequently the way that we go about representing text data. And the big problem with this is that if we have a dictionary with like 100,000 words, we are going to be hurting pretty bad for space, because that is just enormous. Like most of those digits in our vectors are zeros. So this is kind of the big problem with text data, is like, how can you, at least in this naive form, the problem with it being like space efficiency. Like it's incredibly inefficient to have 100,000 dimensional one-hot vectors, one for every single word in our dictionary, you know. So yeah, we'll talk a little bit about text data a little more later. But are there questions on like how we're representing like sequence data, or like text data specifically? Since that's probably like the easiest one to like think about and reason about. Yes, friend.
So as now,
Yeah, yeah, they're definitely chunky. So yeah, so again, just like with audio data, rather than just looking at every single one of our like maybe 2,000 per second samples and looking at the pressure at that little slice in time, we're going to try and figure out a little bit later how we can better represent each of these words, so that instead of a 100,000 dimensional vector, we have something a little bit smaller and maybe more meaningful. Yeah, good question. Are there any other questions? All right. So we should talk here a little bit about like, what are the goals of sequence modeling? Like, what are we trying to do? What is it about a sequence model that can't necessarily be captured by like our regular, just vanilla deep neural networks that we learned about all the way back in like the first week? So like the first thing is arbitrary length data. Sequences can be arbitrarily long. A sentence can be arbitrarily long. A book can be arbitrarily long. If you have access to different slices, different lengths of like weather data, we would still like to be able to process all of those, even though the lengths are different. Whereas with our normal computer vision models, with our standard deep neural network, right, we fixed the size of our input. And if you got an input that was of a different size, we would start getting errors, and it was something our model just couldn't handle. So we'd really like to be able to handle data of like arbitrary lengths. So there's also different like paradigms. There's cases in which we can have an entire sentence and we want to output a single value of like sentiment. Like, is it happy, or sad, right? So this is a case where we have a really long sequence and we want to output like a single value. Or you can have like translation. So if you have a sentence in English and you want to output like the French translation, that's a case where we have an input sequence of a variable length, and we would like to be able to spit out another sequence of variable length. But it gets more complicated than that too, because our English sentence might not have the same number of words as our output French sentence. So we need to be able to handle not just variable length inputs, but also variable length outputs, depending on like what kind of thing we're modeling, right? This is kind of a weird one. Do people have questions about this? Yeah, okay. So there's different, not just sizes of inputs that we might want to model, have our model be able to take in, but different sizes of outputs that we would also like to be able to get out from our model. And obviously that was something that like our CNN couldn't do. Our ConvNet could not spit out variable number of like classes for any one input. We always spat out the exact same number of digits from like our deep neural network, our standard deep neural network. And also like long distance relationships. So for example, like on this text example, you have these sentences the worst food I've ever had was from this restaurant, and the best food I've ever had was from this restaurant. If you're trying to figure out at the end of the sentence, if by the time you get to the end of the sentence, you're wondering like, did this person have positive or negative thoughts about this restaurant? You need to be able to figure out, you need to be able to look all the way back or have information all the way back from the very start of your sequence. We need to be able to somehow connect ideas that are on very different parts of the sentence. We need to figure out how to like connect these two together. So that's sort of the other thing that we need to be able to handle. Whereas like with CNNs, we only cared about like what was in the little region of our filter, right? Neighboring pixels is the thing we were more concerned about. So how do we do 1 and 2 while still handling like big long distance relationships across arbitrarily long sequences? So these are like the 3 primary goals of like sequence modeling that we would like to be able to handle that our standard model, our standard like deep neural network can't really do. Do people have questions or comments or concerns about this? Thoughts? All right. So we're going to talk here about recurrent neural networks, which is our sort of first pass attempt. They kind of work, but not particularly well. There's like a lot of issues that they have that stop them from performing well, but they will cover all of those 3 goals that we'd outlined that we would like our sequence models to be able to accomplish. So again, like why does our naive thing not work? We can't have variable length inputs. Like your sentences, if every single word is like an element in a vector, if we have a sentence as an input that is slightly larger or slightly smaller, it's not going to make sense for a neural network. We're not going to be able to handle it. So again, that is the problem that we're currently facing. And so this is our first pass attempt at solving this. So recurrent neural network is going to have basically this cell, like this A value, that is shared across every single sequence element. So in this case, we have x0 as our first token, x1 as our second token in our sequence, and so on and so forth, all the way up to the very last token, xt. So what we're basically going to do is at the first time step, x0, we're going to feed that into our cell A, and our cell A is going to spit out like an output h0 and also some information to share with our next cell with the next step. And we're basically going to continually processing our next sequence element and pass in what we learned at this time step to the next cell, where we're going to process it again. All of these A's are going to have some learned weights in them. There's going to be some stuff going on. There's some deep learning stuff. We're going to have weights that are learned in there. But the important thing to note is for every single cell there, A, they all have the exact same weights. They're all shared. It's the same cell on the left that's processing every single input element in our sequence. So again, this is what we have. X0 could be the, and then quick brown all the way to dog, right? And these are all like one hot vectors or whatever. And say if we're doing like sentiment classification, then something we can do is just pay attention only to the very last guy out of our sequence. So we're going to pass in our cell A is going to spit out an output as well as information to the next cell. When we process quick, we take in the information from the earlier part of our sequence, right? Spit out something else and information for the next step of processing as well. Do people have questions about this so far and like what's happening? Don't worry about like what's happening inside of A, but like the thing to understand is that it spits out H0 and a second vector as well that gets fed into the next guy. Do people have questions about like the mechanics of like what we're doing here to some degree? Yes, friend? The output? Yeah, so like if these are like H0 is a vector, H1 is a vector, H2 is a vector. So yeah, you can choose how to interpret it. So if you want to interpret it as like the probability of like any given word in our dictionary, then it could be some kind of like translation thing. where H0 is like a vector of probabilities of being like the French version of the word the, or any other word in French. They could be probabilities of the translated word. Or if we're doing like sentiment classification, then we just ignore everything except for the very last guy in our sequence, HT. And then we see like, we interpret the output as like how happy or angry we thought the input sentence was. So yeah, they're all vector outputs. And we're gonna choose like how to interpret them. Does that make any sense?
Yeah.
Okay. Yeah, and how we interpret them and whatever loss function we put on top of that is going to determine how our network learns how to output proper, good looking outputs. We can also like stack them too. So A and B both have independent weights, but all the A's share the same weights, all the B's share the same weights. So you can have multiple layers, so to speak. So your H0 isn't an output so much as it is the input to your next layer in this RNN. Yeah, this is sort of a little bit of a strange concept, but it's basically like your hidden layers. Yeah, we're just taking our sequence output of H0, H1, H2, feeding it in to another RNN basically, and then reading the outputs at the very end. So that is like the basic form of an RNN. So to kind of peer under and see like what's happening. So we take in like a sequence element, and we're very basically, because all of our sequence elements have the same length, every word in our dictionary is a one-hot vector of the same length. We can just do sort of like a linear layer on it. We do a linear layer on the information we took in from the previous time step and our input at this time step. So we have our A here, and it takes in like H1, and then the output from the previous layer, right? And what we're simply going to do is just do a matrix multiply for both our input and the output from our previous layer, just like a linear layer, and then basically, yeah, just stack them on top of each other or add them together. Yeah, and then we do a tan H just to make sure that all of the outputs from this are going to be in a reasonable range from like -1 to 1. We'll talk about this a little bit more later, but it boils down to making sure that when we do repeated multiplications in our back prop, we don't have values, or even in forward propagation, that like blow up or get super small. Yeah, so it basically boils down to taking in our input at this time step, multiplying it by a matrix, taking the output of our previous layer, multiplying that by a matrix, adding them, and then spitting it out. Are there questions about this? Yeah. So again, it basically boils down to doing a simple linear layer on our previous activation and our current time steps data. Just to do some kind of processing on it, and hopefully the values inside of our weight matrices here, WHH, WXH, hopefully they learn good values that will spit out meaningful data, especially when you start stacking multiple layers effectively. So you have A leading into B. More of these you start stacking, the more complex sort of functions you can start learning. Yeah, are there questions about sort of the mechanics that are happening here? Okay. Yeah, and again, the thing I want to emphasize is like the tan H is there because what your output ends up becoming, so you have like X0, X1, and then all the way out to like Xn, right? The output from here was the output of a whole bunch of matrix multiplies, all at every single step, that led into Xn, that then got outputted. And if after every single output, our value is like really large, like 100 or -50 or like 3000, right? All of these multiplies start to get really out of hand until your value that you take in at your very last cell is just going to be gargantuan. So by doing a tan H on the output of every single cell, by doing a tan H on the output here and here, we make sure that the values are between -1 and 1. So when we're doing all of these repeated matrix multiplications, things don't blow up too badly. Yeah. So did we achieve our goals for this sort of very basic attempt at trying to make a sequence model? So we can handle arbitrary length data since every single A has the exact same weights. They're shared. We can handle any arbitrary input size. So in that sense, we have succeeded. We can also handle output sizes of variable length. Our model, we can choose to only look at some of the outputs from our model. Yeah, we can look at the very last output from our model. We can look at all of the outputs, all of the output H's from our model. We have variable output lengths too. So in this sense, we have succeeded just by choosing what we want to pay attention to from our model. And in theory, we can handle long distance relationships as well. In that after we processed our first token x0, we outputted some information about what was here and what has happened in the earlier parts of our sequence. As we go deeper and deeper, we are passing information. And in theory, if our network chooses to use that information wisely and doesn't distort it over time, in theory, we can pass information from earlier in our sequence. So we've this is our naive attempt at trying to create some kind of sequence model. And just to be fair, this isn't something that's like really used, and it's not something we're going to use too much. But the hope is just that it sort of gets you thinking about these 3 challenges in sequence modeling that we kind of care about. And an attempt at getting you to see like one possible naive solution that will work. Do people have questions? All right. Yeah. So it's not like mission critical that you sort of understand like this math, but just this idea that you're processing the first token, passing some information to the next step, processing the second token, and using the information from earlier in our sequence as we go. Yeah. So that's the sort of important thing that I want to make sure y'all take away from this portion, more so than the actual architecture. Yeah. So on to the next section, embeddings. We talked a little bit about how like text data, if you have a dictionary with 100,000 words, every single token here, x0, x1, all of these are of size 100,000. It's a 100,000 dimensional one-hot vector. And that's kind of just insanity. To pass a 100,000 dimensional vector through like a linear layer, it's just a lot of unnecessary compute. And we'd really like to find like a better way to do things. So like one thing you could try is like representing each word with like binary, for instance. So like for the 1,000, or for like the I don't know, 5th word in your dictionary, instead of representing it as 0, 0, 0, 0, 1, and then more zeros, instead maybe represent it like with binary, which would be what, 5, which would be like 1, 0, 1, I think, something like that. 1 plus 4, yeah. So maybe represent it with like binary. It's like another. The idea, this maybe doesn't work super well, but the idea is that we're trying to figure out like something that still has all of this information, and still makes all of our different outputs look distinct, but something like more compact, like more reasonable. So there's like a lot of different choices you can try. You could try encoding the word from one hot to like binary, or like trinary or something else that's like really wild. But how do you know like which choice is best? Rather than trying to choose which thing is best, let's just learn a better representation. This is deep learning. So let's just throw deep learning at it. So for every single word in our dictionary, instead of feeding in the one hot vector, for every single word in our dictionary, let's just learn a smaller vector that we can then feed in. So if our word here is like dog, for instance, we're going to have like a little code book, and we're going to go in our code book to the vector that represents dog, a vector that is learnt, I should say. All the parameters in it are learnt, and we're going to pull that out and then feed that into like x0. Yeah, so these again are still like parameters that we can learn. It's just going to allow us to compress the representation from being length 100,000 to something smaller, like maybe length 128. So the word dog will now be represented. Whenever we see the word dog in our sentence, what we're going to feed in is the learned 128 dimensional vector corresponding to the word dog. Yeah, do people have questions about the idea of like text embedding? Okay. Yeah, it's basically just finding a more convenient learned way to replace our enormous one hot vectors. Yeah. Yeah, it's fundamentally about reducing dimensionality, and rather than passing this giant vector through like a linear layer immediately, let's do a lookup on our code book to find the smaller version of this 100,000 dimensional vector. And the hope is that these inputs will be sort of like intelligently compressed. So maybe the words cat and dog are sort of closer together than the words cat and like grass. So hopefully they're sort of compressed in an intelligent way too. And there's some interesting things on that you can go and like Google, or we can talk about afterwards. Yeah, so if there are no questions, it's only one little last section. Yes.
You said that they were learning like better representation on one hot code.
Yeah.
Does it take in that one hot coding vector to learn it, or does it just
Yeah, so just like well, we're literally just going to like hard code just if the word is equal to dog. Then instead of creating this one hot vector and inputting it, we're just going to like, wait, could you explain what you mean a little bit more? I think I want to make sure I understand your question fully.
I think you had mentioned that like you will create a better representation, like cat and dog close together.
Yeah.
But like, how does it know if it's like better than one? Like, it doesn't know. We're just hoping that it's better than one hot code. It doesn't actually have one hot coding as a comparison, or
Yeah, so like, well, like say, like, okay, so say we're taking 100,000 different words and we're going to embed them in a two-dimensional space. So every single like 100,000 dimensional input here, like the word cat, dog, Paris, Rome, whatever, all of them, we're going to go to our code book and we're going to look up what we currently have for our embedded representation, right? So they're all just like two-dimensional vectors that you can like plot. And so the hope is that maybe like cat and dog are like probably kind of close together because they kind of both mean like about the same thing, like small furry creature running around. And then like completely in the opposite direction might be something again like grass. And the hope is that if our model here, if say the task we're doing doesn't really require a distinction between what cats and dogs are, if they're both like if the task is like I don't know, classifying like how good or how positive or negative like a restaurant review was, distinguishing between the words cat and dog are probably like not particularly important. So when we actually do backpropagation, we might find that like the gradient to this embedded vector kind of moves cat and dog maybe a little bit closer together than they were previously, because there's not really like an important distinction between the two. So the hope is that by doing gradient descent onto our code book of embedded vectors, the stuff that are sort of similar will get kind of moved closer and closer together. And like maybe the word grass gets moved really, really close to the word like weeds, or like flower. So like at the very beginning, when our code book is randomly initialized, the word flower might be way over here. But as we start doing gradient descent, it'll get moved over slightly, and everything will start getting moved that is like semantically similar together. Does that make a little bit of sense? Yeah. Okay. Did that answer your question?
Yeah,
Did.
it did.
Okay. Yeah. So yeah, it's this code book that we're going to be doing gradient descent on. Hopefully things that mean something similar will kind of move close together, and things that mean very different things will move far apart. Yeah, there's like some interesting work. What is it on? Is it word to vec?
Yeah. Talk about word
Yeah.
and pretty lecture. But what I find out, like if you have two vectors that are close together, you can use the animal movement of measure also when you are.
Yeah.
This is called broken security of the before, but that can be a good one. Called maximum.
Yeah, like how close they're together. And there was like some interesting examples on like someone training on like a very large thing of text, just calculating like embeddings for every single word. And there were like, it was interesting that, what was it, like the distance between the vector from like, I'm gonna, hold on, let me erase this here. There's some interesting things that like, again, like it wasn't a two-dimensional embedding, but let's just say for the sake of argument that it was. Like the distance between like man and woman, like this distance here, it was like the same direction as like king and queen or something like that.
Right. So you could do something like king minus man plus woman, and you would get something that's very close to the word that you would. That's kind of like kind of that here learning the word that kind of it's trying to learn the meaning. So I'm trying to put that king and queen at a similar distance.
Yeah, I don't know. There were just some interesting things like this, like the distance between the two is like the same. There was, yeah, there's some cool stuff that happens with like word embeddings. Yeah, that was kind of just a fun little thing. Yeah, are there questions on like any of that stuff? All right. Yeah, this is a somewhat shorter lecture, so there's only like one last little section to go. So if there's any questions, or if you want me to go back at any point, like please feel free to let me know. We can have a little discussion about sort of like this idea of like embeddings and stuff like that. Yeah, so the last section, positional encoding. So like how much time has elapsed like can matter, like what position we are in our sequence can matter. Like it's not maybe probably as important for like text data, but in a lot of domains, like what time of day something happened might matter. Yeah, like the timestamp can make a significant difference. And we would like some way to feed in like a timestamp. And sort of the naive approach again is maybe like one hot embedded vectors for like feeding in the timestamp to make sure that, again, all of our timestamps look distinct. So that might be like the naive approach. Something maybe slightly better might be like binary. So it's basically looking for how do we represent a one hot vector that maybe represents something. Yeah, this is like the 0th element. This is the first element in our sequence. Second, with the idea being that we take this one hot vector representing the position that we currently are in our sequence and just concatenate it on to every single element in our sequence. So we just concatenate on a little timestamp that currently would just be something one hot. We'd like something slightly better. Binary being another not terrible approach. But what we're gonna end up doing, what ends up working pretty well is called well, actually we'll talk about what works here in a second a little more. Binary first. So you can do learned positional encodings, but we're not going to do that here because we have something that works a little bit better. The analog way, you can see every single element if we have like a max sequence length of like 16, in this case, you can append on like a binary representation of where we currently are in our sequence. So if you're at step 0, you would append on 0, 0, 0, 0. If you're at step 1, 0, 0, 0, 1, and so on and so forth, like the binary representation. Pass this into our network and hope that it can understand from that, like how deep we are in our current sequence. Yeah. Do you have questions about the idea of like appending this like binary encoding that serves like a timestamp, like how far along in our sequence we are? Does anyone have questions about that sort of broader idea specifically first? Yes.
So there are a lot of like for say, I don't know, like dog.
Yeah.
At like word number 2 versus like word number 20.
Yeah.
So,
Yeah. Yeah, basically. Which it's sort of unintuitive for like text because like the word, like how deep in a sentence the word dog is probably like doesn't add much meaning. But in the case of like weather data, if your weather data always starts at like 10 a.m. And you're trying to predict like the temperature, like time of day probably factors into that pretty heavily. So it's probably worthwhile to stick on a little timestamp that represents like, oh, this is the 2nd hour since we started measuring this morning. Does that make sense? Yeah. Okay. Yeah. So on a slightly deeper level, if we're looking at like what's happening here, if you look at the red column as we're going deeper and deeper into our sequence, it's flipping every other one. As you go from 0 to 1 to 2 to 3 to 4, it's just flipping back and forth. Every single element, it's just flipping. And if you look at the second most significant digit from the right, it's still doing flipping, but it's just flipping every other one. And if you look at the green column, same thing. It's just flipping back and forth, except now at half the frequency. And same thing for the yellow. And the problem with doing maybe like a binary encoding, like the reason this is like somewhat undesirable, is because if you would like to still use a length 4 positional encoding, but your max sequence length is like 32, you're sort of out of luck because if you have 4 digits, you can only represent 16 different unique time steps. Yeah, that's sort of the intuition for why we would like to do something that isn't binary. And the question is like, is there a continuous analog of this so that given only like a length 4 vector, can we somehow encode like maybe 32 or 64 or 128 different encodings into like something small like that? So since this is basically just literally flipping back and forth like a sine wave or a cosine wave, what we're going to append will end up just being sine waves and cosine waves with different frequencies. Yeah, we're simply going to replace every single vector entry instead of just being like the binary 1 or 0 with sine or cosine of slowly doubling frequencies. So omega 1 is going to be half of what omega 2 is. Omega 2 is going to be half of what omega 3 is. Every other entry you go down, you're going to double the omega. So we've basically just found like a continuous analog. So our red column, the frequency is like 1. It flips like every other, I guess it would be, what would it be? I don't know. But it's flipping every other one. The blue column is flipping with half the frequency. Same thing for green, same thing for orange. So we've just found sort of a continuous analog where we're not flipping back and forth between whole steps. We're not flipping between entirely like 1 and 0. We're going to slowly decrease and then slowly increase again, flipping back and forth in a continuous way. Yeah, we've simply replaced our 1s and 0s with sines and cosines that are still going to flip back and forth, but just now between 1 and -1 instead. Do people have questions on like this idea of trying to find like a sort of continuous version of like a binary encoding? for like a time step at a certain point in time. Okay. Yeah, it's sort of a weird concept, but if we're at sequence element 1, we're just going to set t is equal to 1 and just evaluate sine and cosine at all of these different frequencies at t is equal to 1. And then at time step 2, we're going to set t is equal to 2. And if we like graph all of this out, this is what we'll end up sort of getting. So every single row is the ith positional encoding, and every column is the continuous version like of our ones and zeros. So like if you look at like any given column, just like the columns up here, like the columns red, blue, green, yellow. So if we look at the columns on our like continuous version of that, if you look on the right, it's doing the same alternating thing between low values blue, I'm sorry, high values blue and low values red, just alternating back and forth as you go along in our sequence. So we basically just found sort of a continuous analog for doing like a binary positional encoding to append on to all of our elements. It's sort of it's kind of a weird thing. And if you have questions to make like on your own, feel free to go back and like take a look at the slide decks. And think about why this right here evaluated at different values of t will just give you these things here on the right that just slowly alternate back and forth. Yeah, are there questions on positional encodings? This is definitely like one of the weirder concepts. Okay. If not, then that is all for today. I will chill up here and y'all can come up and ask more questions and stuff. But yeah, that will be it for today.